Okay, I'm sorry, we're recording, so I wouldn't tell you when that picked up or immortalized on YouTube. So we've had some interesting things captured there. Well, the other day in my other class, I had to edit it to cut out a rant that I made in class. So, yeah.
Make said rant tonight.
Yeah. So, yeah, it's hard to be in almost spring break mode, but yeah. Okay, how's homework coming?
It's coming. I got half of 5 done.
Okay.
We've been working on 2 different problems. She's been working on 1. I've been working on 5.
Okay.
So,
Yeah.
But
Well,
at this point, I just need to go back and write the pseudocode for
Okay.
costs.
Yeah. Well, you're getting here with number 1, so you're getting there.
Yes.
So, okay. Yeah. I like the creative approach.
Call it creative.
Well,
I think I happened on it by accident.
okay.
By
That's
chance.
part
Okay.
of creativity, though.
Yeah.
Yeah, that's how these things happen.
Cool. Well.
Yeah. A
hopefully it's
lot of successes in that happen by accident.
by chance.
So, I guess a preemptive comment about number 3, because I think one of the difficulties people have is just maybe the problem should be worded a little better. So I guess another way to describe it is how to solve the actual given system is By equals C. By solving systems involving A, since A is an approximation to B, so solving any system, so for instance, solving AY equals C would approximately solve BY equals C. And you are including in your method the iterative refinement algorithm, but you're just tweaking it a little bit. Because the thing is with iterative refinement, you're solving a system to get an error estimate. And you're trying to solve a system involving A, and you're actually using A in iterative refinement. But because of round-off error, when you're solving a system, it's always with an approximation of some kind. So here you're given that A approximates B, and it doesn't really matter in what's the reason for the error. The point is it's an approximation. So okay, I'll stop there in the interest of not giving away anything more. But that's the idea, because it says in the problem you have a fast algorithm for solving AX equals B. The point is that that's generic. Any system involving A you can solve quickly. Okay, but you have to keep in mind that this is what you're really after. And you have to keep that in mind when determining error. Okay. All right. So that's the real prize there. Okay. So we'll see how this goes. But yeah, 3 always gives people the most fits. Okay. I forgot. I wanted to mention. So we have our Siam Student Chapter T-shirts.
It looks so
I know they're awesome.
Yeah. So for $10, so you contact our Haley Dozier, our chapter president, who has them. And the nice thing is, for this class in particular, you guys actually know what the caption means. So, watch out, we're ill-conditioned and unstable.
Yes.
So, in fact, you guys would be the only people on campus who know the meaning. Okay. So now, speaking of solving systems, we're going to conclude our discussion of solving systems by direct methods. So I talked about one special class of matrices last time, positive definite. But now the other one, that's also very important applications, banded matrices. Okay. So first some definitions. Okay. So matrix A has upper bandwidth P if Aij all the entries out of Aij are 0 whenever J minus I is strictly greater than P. So for example, if so to give an example of this, so here's your main diagonal, and then you have X a little off. So here we have a case where P is equal to 1. So Aij is equal to 0. So we can have anything we want down here, because we're only talking about upper bandwidth. So down here is allowed to be 0, but up here must be 0 for J is greater than I plus 1. Because here we have, on the main diagonal, is where we have I is equal to J. Here on the super diagonal, so right above the main diagonal, we have J is equal to I plus 1. So if a column index is any greater than that, you're out here, where it's 0. So here we have a case of upper bandwidth 1. All right. Similarly, A has lower bandwidth Q if Aij is 0 for I minus J greater than Q. So when I is greater than J, you're in the lower triangle. When J is greater than I, you're in the upper triangle. So I always keep that in mind, keep track of like where I am in the matrix. Okay, so the so then the total bandwidth is P plus Q plus 1. So you're accounting for upper bandwidth, lower bandwidth, and then the plus 1 is because you also include the main diagonal in the bandwidth. Okay. So if this total bandwidth is less than 2n minus 1, which is that's the total number of diagonals you can possibly have, because you have one main diagonal, and then you can have n minus 1 upper diagonals and n minus 1 lower diagonals. So if you don't have stuff in all of the diagonals, we say A is banded. Now, we're most interested in the cases where the total bandwidth is actually much less than 2n minus 1. So, for example, a case of particular interest is if both the upper and lower bandwidth are equal to 1, so you have a main diagonal, the super diagonal, and a subdiagonal. We've actually probably brought this case up before. A is tridiagonal. That comes up in a lot of applications, especially for differential equations. Another one that actually has come up now and then, like seen in research, is if they're both equal to 2. So then you have 5 diagonals in total. So we say A is pentadiagonal. I'm not aware of any fancy terms beyond that. Like, for instance, I came across a case where P and Q are both 3, and they just say, oh, it's 7 diagonal. So I guess they could call it like septa diagonal if someone really wanted to, but everybody would be like, what does that mean?
What's the difference in these and like a sparse matrix?
Okay. A banded matrix like this, where you have particularly low bandwidth, that is a sparse matrix. So it's like an example of a sparse matrix. But you can have other sparse matrices. Sparse just means most of the entries are 0. But the non-zero entries could be in some random pattern.
Gotcha.
Yeah, so...
But don't they look like, don't they kind of look like these diagonal matrices?
Often,
Yeah.
yeah. It just depends on the application. If you get to... if you're solving 1D differential equations, you tend to almost always get banded matrices. If you have, once you get to 2D, you might have a part that's banded, but also you have these other entries that are out there somewhere. And then there's some applications where it really is random as to where the entries are. So banded is sparse, but sparse is not necessarily banded.
Right.
Okay. All right. Now, there's something else I can mention. Besides what I have coming up next in the notes.
About sparse matrices?
Well, it occurred to me. Oh, okay. Now I remember what it is. Oh, but I think it's actually later in my notes. Okay, but I'm just going to wait then. I just want to make sure I don't leave out anything. Okay. Now, so it turns out that when we have a banded matrix, Gaussian elimination can be a whole lot more efficient than in the case of a general matrix. Because, remember, Gaussian elimination for a general matrix, it takes 2/3 n cubed floating point operations. So if we know what the bandwidth is, P or Q or whatever, then what can we say about the cost of Gaussian elimination in that case? So if P and Q are order 1, and what I mean by order 1 is they're not related to n. So there's some particularly small value that, like for instance, a tridiagonal case or a pentadiagonal case. So in that case, Gaussian elimination and also the 2 substitution stages, forward and back substitution, each require only order n floating point operations. So when it's banded, most of the entries are 0, you expect to have some savings in operations, Gaussian elimination, but we actually eliminate 2 orders of magnitude, not just 1. Okay, so because what we can say is if A has lower bandwidth Q then so does L. So in your LU decomposition, now I should mention we're assuming no pivoting for the time being. I will have to discuss pivoting later. So we're just going to simplify and not do pivoting. So in your LU decomposition, A equals LU, the lower triangular factor inherits the lower bandwidth. And the reason why is you have at most Q entries per column to eliminate. So this is one reason why Gauss elimination is so much faster, because normally you have to eliminate nearly n squared over 2 entries, but now you only have to eliminate roughly q times n. So you've already cut down by order of magnitude how many row operations you need. Now the other thing is, if A has upper bandwidth, P, then so does U. So the upper triangular factor inherits A's upper bandwidth. And the reason for that is you have at most P entries per row to update when you perform a row operation. So you have fewer row operations to perform because of a lower bandwidth. Each row operation costs less to perform because of the upper bandwidth. So the total cost of Gauss elimination is on the order of like n times p times q. So if p and q are both small, it's really order n floating point operations. Okay. Again, assuming that there's no pivoting. All right. Now, we have to think about storage. Don't use a two-dimensional array. That's wasteful. You're allocating all the storage for all of the entries that are going to be 0. And if n is large, you definitely don't want to do that. Instead, use vectors. So p plus q plus 1. So your total bandwidth vectors. So your total storage, so each vector is of length less than or equal to n. Because the longest vector you'll need is of length n, that's for the main diagonal. And then you could use shorter vectors for the other diagonals. So your total storage is less than like p plus q plus 1 times n. So you're talking order n storage instead of order n squared. All right. Now, what I'm going to do is I'm going to show you what happens with the usual algorithms of Gaussian elimination, forward and back substitution in the case of tridiagonal matrix. Okay. So then we have Gaussian elimination. Without pivoting. So first we're going to write out the algorithm as we know it, and then I'll make changes. to account for the abandonedness. All right, so we're looping over all the columns, and then we're looping over all the rows below the diagonal. And then we compute a multiplier, which is Aij over Ajj. And then we loop over the elements of the row where we're doing the operation. And we perform the update on this row. Okay, so here's a regular algorithm, but now to monkey with it, first we take advantage of the fact that in column J, we're only eliminating one entry in that column, and that's the entry J plus 1J. So in fact, this loop is only going the second loop is only going to run one time. I is only equal to J plus 1. So we're just going to do this one row operation. Okay, so I'll leave I how it is, but we know that it's equal to this. So that's one. So now already the algorithm is cut down from order n cubed operations to order n squared. But now we can do better because here we're working with elements like A, J plus 1, which is on the diagonal. So if I translate this, so A, J plus 1 is equal to itself minus a multiplier, which is M J plus 1J times A row J column J plus 1. So that part is going to stay the way it is. But now, let's go to the next iteration, the second iteration. K is equal to J plus 2. Now, this entry is on the super diagonal. So it's non-zero. So I think, okay, we need to do something here. So we have a multiplier, same multiplier. But then I go to row J, J plus 2. Now, this is a tri-diagonal matrix. When A is tri-diagonal, that means that Aij is 0 for really the absolute value of I minus j is greater than 1, because the positive sign, I minus j, that accounts for the lower triangle, and the negative sign to j minus I counts for the upper triangle. So, this entry is 0. So, we actually don't need to do this. So even though this entry is not 0, it's not going to be touched. Not by this row operation, maybe a different one. So that's it. So we don't need a for loop here either. We can say K is equal to J plus 1. So 2 loops gone. So now we see why Gauss elimination takes only order n floating point operations. So now, it's kind of a mess. So I'll write the cleaner version over here. For j equals 1 to up to n minus 1, we need a multiplier. So I'll call this, I'll just give it a single index, mj is equal to a j plus 1j over a jj. Actually, I'm not going to call it mj. I'm going to call it lj for reasons you'll see in a moment. And then I have my row operation, which only does one thing, and that's a j plus 1 is equal to itself minus my multiplier, Lj, times the element above it. So that's a j plus 1. Now, and then that's it. Okay. Now, let's see. So notice, if you look at the indices, either the indices are equal, like here, or the row index is 1 greater, or the column index is 1 greater. So, when the indices are equal, it's on a diagonal. If a row index is greater, it's a subdiagonal. If column index is greater, it's on a superdiagonal. So I'm going to organize the matrix storage. Like, so the main diagonal, I'm going to call that a vector A. And then below it, the subdiagonal, that's going to be vector L. And then the superdiagonal above it, I'm going to call that U. So we're going to use 3 vectors for storage. So, for instance, the first entry of A is going to be A11 and down to ANN. First entry of U is going to be A12, and then the first entry of L is going to be A21. But this is going to be equal to U1, and this is going to be equal to L1. And then this is going to be DN, and then the last entry down here is UN minus 1 and LN minus 1. So now what I need to do is rename everything in this algorithm in terms of, actually, I'm going to call this D for diagonal. Okay. I'll make sure it doesn't look like an A. Okay. So L, D, and U are my vectors. So now I can morph this algorithm again into its final form. So LJ is correct. This is, I'm modifying LJ, which is right here, and I'm dividing it by DJ, the entry on the diagonal, to get my multiplier. And now, so this is what I want to put in my lower triangle. In my LU factorization. And then, this entry is a diagonal entry. So that's dj plus 1 is equal to itself minus LJ again, that's my new multiplier. And then this is UJ. And that's it. So this is all that's necessary, the Gauss elimination on a tridiagonal matrix. So almost literally nothing to it. And you can plainly see it takes order and floating point operations. Any questions about how that evolved from the original god-awful thing?
So this is order n.
Yeah, because there's only one loop.
Okay.
Yeah, whereas here we had 3 levels of loops that took up to order n operations. Yeah. Yeah. Well, in fact, what do we have here? We have 1 division, 1 multiplication, 1 subtraction. So the total floating point operation count is 3n minus 3.
I never think of loop, but well.
Okay, yeah, that's really how you tell. Well, for instance, okay, forward back substitution. We only have 2 levels of loops, so it takes order n squared. Now, that's assuming the loops take up to order n iterations, which they do. these cases. So you have to be careful about that, but yeah.
What if they take more than n iterations?
Like another order of magnitude for a loop, then yeah, you could have something worse. So, or from a bookkeeping point of view, that'd be hard to squeeze it into one loop. Okay. What's interesting about this is, okay, L is changing, the lower subdiagonal is, and the diagonal entries are changing, but the upper triangular entries never do. They're never touched. They're used, they're just not modified. So that's kind of interesting. Okay. So then you can do similar modifications for forward-to-back substitution.
We don't know the relationship between the lower diagonal and up, like the sub, the two off diagonals. We don't know anything about them.
You mean like what this algorithm does to them, or I'm not sure what.
No, like if the matrix is symmetric, then it would be the same, but
Right.
we don't know that for sure. Like, because this is any tridiagonal matrix, right?
Right. Yeah. If the matrix is tridiagonal and symmetric, then I could probably use LDLT, like I mentioned last time, instead of this. Because if you start with symmetric matrix, then you'd like to have a symmetric factorization too. Okay. Now, for forward-back substitution. For substitution, the original algorithm, and this is assuming that L is a unit lower triangular matrix like we normally have from Gauss Elimination. Alright, so you start with your entry of your solution equal to your right-hand side. So this is for Ly is equal to B. And then you have another loop. Oh wait, I minus 1. Okay. Then you have yi is equal to itself minus Lij yj. That's it. So what happens in the case of L coming from a LU factorization of a tridiagonal matrix, L only has a lower bandwidth of 1. So we don't need this inner loop. We can just set j equal to I minus 1. So, okay, and in terms of our, so this is really L row I, column I minus 1, but this is, in terms of our vector storage, it's L I minus 1. So really, now, but the thing is, suppose I is equal to 1. Well, in the old version, this loop just wouldn't run because of the counter variable limits. But now, if I equals 1, this doesn't make sense because we have L0. So here's how it should be written instead. For I equals 1, we just have y1 equals b1. And there's nothing more to do for that one. Then we go ahead and run our loop, starting at 2. And then we do these things. So yi equals, well actually we can combine these in one statement. Yi is bi minus this, li minus 1, yi minus 1. That's it, there's nothing else to do. And we can see it takes order n operations. So really, 2n minus 2 floating point operations compared to the 3n minus 3 that we had for Gaussian elimination. And then we can do a similar thing for back substitution. So in the original algorithm, we have counting down from n to 1, and we set our, so this is for u x is equal to y, so we set each element of x equal to the corresponding element of y to start, and we have our inner loop that runs j equals I plus 1 up to n, and we subtract terms off, minus u I j x j, and then we divide by a diagonal entry. But, alright, so that's the original algorithm. But now, we don't need this loop anymore. We can just say j equals I plus 1. Because u has an upper bandwidth of only 1. So, so now the algorithm is as follows. Our first entry, or well, really xn, is equal to yn divided by well, the diagonal part, which is an, because our diagonal entries are stored in A. And then we have our loop. Then now we'll start at n minus 1, n minus 2, all the way down to 1. And we can do all of this in one shot, these three statements. So we can say xi starts out with yi minus ui I plus 1, which is the same as ui in our vector storage, xi minus 1. No, I plus 1. And then we divide by our diagonal entry, which is in our vector d. Whoops, that's d. I was A in the notes. But, and that's it. That's our back substitution algorithm. So, as for how I converted from matrix entries to entries in our vector storage, so if we're dealing with, for instance, L I minus 1, in our vector storage, that's Li minus 1, because you can see the correspondence over here. The first entry is the 2, 1 entry, that's L1. It's the column entry that makes the difference. Whereas for the upper triangle, it's the row entry that determines the index in your vector storage. So u I plus 1 is referred to as ui, and then our diagonal entry a dii is as thought of as di. Okay. It's very common to make these mistakes when coding these things. You have your nice mathematical description of the algorithm, and you translate that into code, and maybe use different storage. And it's a common mistake to be like off by 1 in your indexing. So it's a good idea to like try out certain like specific examples to make sure you have the indexing right.
So the lower diagonal is always columns, so like, if we're not just doing tri-diagonal, if we're doing like, you know, the penta-diagonal or whatever, it's always the column for the lower and the row for the upper.
Well, if you have more diagonals, well, yes, but there's going to be like a shift. For example, let's suppose if I have another diagonal here, a second diagonal, a first entry, well,
Well, couldn't you just?
actually, it would be, yeah, it would be row index. 'Cause the first entry of this diagonal would be A13, but I would call that like Z1.
Yeah, and then your loop and all that, it would just start like, well, depending on which one, you would just, it would be like, I plus 2 rather than I plus 1 and things like that.
Yeah,
For your
so,
index.
yeah, like for instance, yeah, I have like the entry, like, I plus 2, but that would be like Z1,
Right.
or ZI. Yeah, okay. Okay. All right, so this is how tri-diagonal translates over, or is the most efficient outcome as possible. If you have something like, pentadiagonal, you can do something similar that would still clearly take order and time, so you only need one loop in each case. It's just that those loops would do a little bit more. Okay. Now, I need to talk about pivoting. That's one of the drawbacks of working with banded matrices. Well, not for a tri-diagonal one because, well, all right, if you're trying to do partial pivoting on a tri-diagonal matrix, you have only 2 elements to look at. So you're doing fewer comparisons again. But for banded matrices, pivoting is actually a bad thing. And the reason why is, and you still get the same benefits of having like smaller multipliers. That's why we do it. But it destroys your banded structure. So what could happen is you could introduce new non-zero entries in portions of a matrix where there were only 0 entries before. You're increasing your bandwidth, therefore driving up the cost of Gauss elimination and substitution. And this phenomenon is called fill-in, because that's what you're doing. By pivoting and continuing Gauss elimination, you are filling in the portions of your matrix that were originally 0. Okay. But the benefit of pivoting is not to be entirely ignored, and there are cases where you absolutely need to do it. For instance, if you might divide by 0 otherwise. So one thing that can be done is this can be a workaround. You could try, for instance, scaled partial pivoting. And what that means is you don't pick the absolute largest element in your column to interchange with, but maybe choose one that at least is larger than the one you have. So you could require that your multipliers, instead of being less than or equal to 1, maybe you impose some upper bound on them. So you're still trying to contain them. You're trying to limit the propagation of round-off error through Gauss elimination, but you're being a little more flexible about it. So that's something that can help mitigate the damage caused to your structure by pivoting during Gaussian elimination. So it's a trade-off. By doing something like this, you keep some of your efficiency, you keep some of your sparsity, and you don't get the full benefit of partial pivoting, but you get something. So you want to try to preserve the numerical stability of Gauss elimination of pivoting. Yeah.
Please show me how this scale partial pivoting works, because I think that it covers the whole matrix. So what's the benefit of that?
Wait, maybe it covers the whole matrix, or?
Yes. Isn't it like a scale? It starts from small block matrix and then.
Oh, I think you might be thinking of something different.
Okay.
Okay. Remember how partial pivoting works? You're looking for that part of a column to see the largest entry, and you swap it up to the top. But in scale partial pivoting, you're not looking for the absolute largest, but you want something that's like you'll take something that's larger than what you have, in such a way that instead of limiting the growth of multipliers to 1, maybe like you're okay with multipliers being less than or equal to like 2 or 10 or something like that. Yeah, so the overhead is very similar to regular partial pivoting, in that you're looking through a column.
But how does that guarantee that you won't put zeros where, or like you won't mix up your?
It doesn't. You're still going to lose some of your sparsity, but maybe not as much as with rigid partial pivoting as we know it. So it's a trade-off. Okay. Well, now I'm in an interesting situation because I finished that chapter 4. Up next is Iterative Methods, which I could start in the 21 minutes that we have. I mean, you can forget it all over spring break.
Or we don't want to do that. We
homework
can
for
do
30
homework.
minutes.
Let's do homework. I go to homework.
Okay.
You don't have to help, we just want help. Well, actually,
Yeah, we probably do.
I'm just kidding.
Okay. Yeah, I'm gonna stop at this point because it seems weird to like.
I would totally
Break it up
forget
like that.
everything. I'm just
Hell, even I forget everything. Okay. All right, and not everybody's here anyway. So, okay. So I will
homework.
see you all after spring break.